Hello everyone. In this video, we are going to talk about two-dimensional elements. And specifically, we are talking about the quadrilateral or rectangle basically, as well as the triangular elements. So, if we have a linear rectangular element, it has four nodes and four shape functions. And we have seen it in one of our previous videos, but here we can see it again. So here, small x and small y are the local coordinates, and then capital X and Y are the global coordinates. So the function that we are going to approximate any physical quantity, let's say temperature, is gonna have four coefficients in it. Why? Because we have basically four nodes, so we can get four conditions from those four nodes. So we make sure that our polynomial has four coefficients. And here we have the constant term, the two linear term, and then this term we call the bilinear term. And we can also, as I said, write it as the dot product of the nodal values and these vector of shape functions. And the vector of shape functions at nodes I, j, m, and n are going to be these functions in terms of local coordinates. We can also write them in terms of the natural coordinates, right? In terms of the parameters kc and eta, where kc and eta are defined, as you can see here, based on the x, y, l, and w. And then we can write our shape functions in terms of these two parameters. And if you remember, we put the center of the origin of the natural coordinates at the center of the element, right? And so the four corners are going to be basically the values of positive or -1 for these kc and eta. So these are the shape functions, and clearly again you see that each one of them is 1 at its own node and 0 at all other nodes basically. So the same properties applied that we had in 1D, now we have it in 2D. So this was linear rectangular element. Okay, so along each node, basically, along each edge, sorry, the parameters, whatever it is, temperature, whatever quantity, it is changing linearly, okay? Now, we might have the higher order rectangular element, which we call it quadratic, second order, and here you have also four nodes in the middle of the edges, and so you have 8 nodes and 8 shape functions. And if you write it in terms of the natural coordinates, this time not only you have the linear and the bilinear term, you have quadratic terms here. And it also gets to the product of linear and quadratic. So you have to have 8 coefficients, so you're going to have 8 shape functions and 8 nodal values. And then the corner shape functions, which is at I, j, m, and n, are going to be these functions. And then the edge shape functions, the ones in the middle, k, l, o, and p, are going to be these functions. And the same properties apply here, okay? They are 1 at their own node and 0 everywhere else. So this is the quadratic rectangular element. Now we can go to triangular elements, first linear, then quadratic again. For linear one, which there is only 3 nodes and 3 shape functions, we need 3 coefficients in the polynomial, so it is going to be in terms of global coordinates. As I said, for triangular ones, we mostly deal with global coordinates instead of local. So you have 3 shape functions, and the shape functions are basically determined based on these parameters alpha, beta, and delta, and A, the whole area of the triangle. And these shape functions are, by the way, also the same as your natural coordinates, and they are the same as the ratios of A1, A2, and A3, which are the three areas split by a specific point P, right? So if you move your P to anywhere, then these three areas would change, and the coordinate of P would change, and the coordinate of P is the ratio of these three smaller triangles areas over the big triangle, okay? So sum of these three parameters is equal to 1, and then your alphas, betas, and deltas are given based on the global coordinates of the corners. So you see here that when I deal with global coordinates, I really need two coordinates, x and y. When I deal with natural coordinate, I need three of them, but one of them is depending on the two others. Okay, so you have one redundant coordinate, literally. Okay, but in general, these are your shape functions. As I said, it's always easier for triangular elements to define everything in terms of global coordinates. But for triangular ones, it's most of the time easier to define everything in terms of the natural coordinate. Although here we also have a natural coordinate as well. And then, of course, we have the triangular element, which is quadratic. Now we also have one node in the middle of the edges. So we have 6 nodes and 6 shape functions. And the 6 shape functions, again, based on the natural coordinate, they are given, as you can see down here, okay? Based on the KC, eta, and lambda. So, these are the 4 most commonly used 2D elements that you can use in finite element. There are others, but we're going to skip those for the sake of time. So the next problem that we're going to see as a real example is analysis of 2D heat transfer problems. So the governing equation is gonna be basically inside the physical material is gonna be kx second derivative of t with respect to x plus ky second derivative of t with respect to y plus q dot, and q dot is basically the amount of heat generated per volume, okay? So this term is going to be 0. So this is basically the net heat coming inside the element and outside, right? So this is some of the inside and outside. And here we can assume that the conductivity of the material K is not the same in X and Y. Most of the time, these two parameters are the same. But if the material is not isotropic, then these two could be different. And Q dot, as I said, is the amount of heat generated inside the material, inside the volume, per volume. So if there is some heat source or heat sink in the part, this number is going to be a positive or negative number. And then there are different boundary conditions. We can have constant temperature at some edge, right here, for example, on this vertical edge, where x is 0 and y can change, then the temperature can be held constant. We can have basically the condition where the material is perfectly insulated on that edge, and then that means the derivative in the x direction for temperature at that location is 0. Now, if the edge is horizontal, right, if you have a horizontal edge like this, then the derivative of temperature in the y direction is going to be 0 for that direction, okay? Which means the heat flux, Q double prime, right, which is in this case ky times that derivative, right? That should be equal to 0. In this case, this is kx times that, right? But kx is a constant. We can cancel it from both sides. So the edges could be horizontal or vertical. In this case, we just consider vertical edges. Then we have a constant heat flux through that boundary. If we know how much that constant heat flux is through that boundary, then this is the equation for it. And if basically it's just an element like anything else, So the heat coming through it is equal to, the heat coming out of it is equal to the one that is given to the environment by the convection, right? So it is subjected to convection, then this is the equation, right? Which is the heat coming in this direction is equal to the heat going to the environment through what? Through the convection, okay? So this is the Newton's cooling law. So these are different boundary conditions that you can have, and this is your governing equation, second order, and it's linear, right? And this is your basically non-homogeneous term in general. So here, if we want to formulate this problem, we are going to use the Galerkin's method, just like we did use it for 1D problems. And then what we do is at different nodes, we are going to calculate the residual terms, multiply them by the weighting functions, and set them equal to 0, right? And if you remember, the residual terms are, we guess some t as a function of x and y, so we guess some t of x and y in this case, and plug it into this differential equation. And since it's not exact solution, the right hand side is not going to be equal to 0, so we call that a residual term, which you can see here, and then multiply each residual term by the shape function or the weighting function of that corner, that node, and call it the residual term for it. And the goal is to get these all to 0. So then we can write all of this as the residual term for that location times vector s, and vector s here is clearly Si and Sj, and then Sm and Sn transpose, right, in this case. So that times the residual term dA equals 0. So we get this vector equation, and then we have to do a lot of manipulations here. If you remember, S, I, J, M, and N are these 4 functions that we had up here, right? These 4 functions. So we plug them in, or in terms of natural coordinates, these guys. We plug them in, we perform the integrations. The t that we have is going to be basically this function, right? So we plug them all in, we do the integrations over the elements and over the area of the elements and set it equal to 0. Here there is a lot of mathematical manipulation until you get the conductance and the thermal load matrices. So going from here to these results down there, there is a lot of algebra involved, and I'm gonna skip those. If you want, please refer to the textbook for more details, and it uses the Green's theorem, okay? So it is going to use the Green's theorem in order to find the matrices that you can see down here. So for derivation, please refer to the textbook. Now here, depending on what element you have, you're going to get what? You're going to get different matrices. And the elements we are going to be using here are linear elements. Okay, we are not going to go to quadratics, just linear elements. So I can add something here with linear rectangular elements. Formulation is going to be this, that the conductance matrix for each element has 2 terms that you have to add together. One is due to the conductance itself in the x and y direction, and this is that term here, right? So just because of conductance from one element to the other, each element has a conductance matrix, which is sum of these 2 elements. This is for x direction conductance, this is for y direction conductance. And also the convective boundaries, the edges of the rectangular element that they have convection with the environment, they also have a T term and they contribute to the global conductive matrix. Because remember, at the end of the day, the goal is what? We want something like this: K global times temperature nodals equals to the thermal load global. Okay? So whatever that has a T in it in the differential equations or the boundary conditions, whatever has T in it will be contributing to what? To this global conductance matrix. And of course, you clearly can see that these two terms will have T in them, so they would definitely contribute to the global K, and these are the contributions. The other things that will contribute, as I said, are what? Are the convective boundaries. And where is it that they have T? Here you can see that convective boundaries, they have a T term in them. Okay, and because of that T term, so there should be some contribution from these to the conductive matrix, and the H term should appear in that. And this is exactly what it is that you can see here. These guys are going to be your contributions from convective boundaries. Now, what are these? Each one of these formulas is for one of the edges. If the convection happens through the ij edge, then use this term. If it's happening through the jm edge, through the mn edge, or through the ni edge, then each one has its own matrices, right? Go back to your triangle here, right? You see that I have ij edge, I have jm edge, I have mn, and I have ni edge. So depending on which one of these has what? Has convective heat transfer to the environment, then you will use one of those. If all of them do, then you use all of those, okay? And you add them together. So here is the contribution, right, from the convective edges, okay, depending on which edge it is. So some of these terms, this one here and this one, some of these is gonna give you the global K, the elemental K, and then when you combine the elemental K, you will get the global K, of course. So the elemental K is gonna be the combination of these two. Now, what about the thermal load, the right-hand side for each element, right? How would you get that one? So the convective boundaries, of course, they have an elemental thermal load matrix. And again, depending on which edge is doing the convection, then one of these terms is going to be applied, right? Also, depending on the heat generated inside the element, you have another term, right? Which is this guy here, okay? And so if there is no heat sink or heat source in the element, inside the element, then this term is zero because Q dot is zero. There is one other boundary condition that can lead to thermal load, and that is if there is a constant heat flux, and that is this boundary condition here. If there is a constant heat flux through that edge, Q naught double prime, then that can also lead to a thermal load clearly. And that comes from these matrices here. Again, depending on which edge has the constant thermal heat flux, then one of these or some of them can also be applied. So this one can also lead to what? Thermal load. Okay, so here we have seen the elements of thermal load, and depending on which one exists, we have to add them together. And then we have the conductance elements, right? These are for what? Linear rectangular elements. Now, we can also use what? Triangular elements. And again, when I say triangular, I'm talking about linear triangular element, not the quadratic ones. So here, very similarly, the conductance elements are going to be these. So this is due to conductance. And the convective boundaries contribution to conductance are these, one of these, depending on which one of the three edges, ij, jk, or ki, will produce that T term. So these two are going to contribute to the conductive matrix for that element. Then for convective thermal load, right? These are the contributions, again, depending on which edge is doing it. And then we have what? We have the heat generated within the element. And then we have, if there is constant heat flux, then we have these. Okay, so similar terms here compared to the triangular element, but you have 3 instead of 4 because you have 3 edges and 3 nodes. And these betas and deltas are the exact same betas and deltas that we had up here, these guys. Okay, so these are the matrices that you need to analyze the heat transfer problem for triangular and rectangular. And you might say, is there any situation that I need to use both of them, both triangular and rectangular? The answer is yes. And you can see that in this example here. So this is a chimney, and inside of the chimney is 100 Celsius. Outside of it is exposed to the air with H of 20 and 30 degrees Celsius temperature. Kx and Ky are the same, 1.4. We want to determine the temperature distribution within this 2D cross section, right? And at the steady state. And of course, here we are only dealing with the steady state. Here we are not dealing with what? With the change in the temperature. Okay, we'll see the transient heat transfer problems in what? In one of my next videos. All these are steady state. So let me add something here. So analysis of steady state 2D heat transfer problems. We are not talking about transients here. If there was a transient, then we also need to consider the C term, right? The basically thermal capacity term and the change in the temperature, right? So here we don't see that, and that's because here we are only talking about steady state heat transfer problem. The same applies for my previous video where I did 1D elements. So now this problem is symmetric. If you look, this problem is symmetric, and it has 8 pieces that they look like this. There are trapezoids. And the problem is completely symmetric for X and Y axis. So we don't need to analyze the whole domain. We just need to analyze one of these what? One of these 8 trapezoids. Everything else will be symmetric for that. So that's what I do. And that's why I'm going to what? I'm going to analyze only what? One of these in here. Okay. So let's go ahead and analyze only what? One of these guys. So the dimensions are what? So since the whole thing is 60, then this dimension is 30, and since this middle part is 20, this dimension is 10, right? And here we're going to break that trapezoid into 3 rectangular elements and 2 triangular elements. So the dimension for each one of these is 10, 10, 10, okay? So we have 5 elements, 3 rectangular, 2 triangular, and we are going to analyze the heat transfer within that 2D medium. Okay, so let's look at the conductive matrices for each element. So here, if we look at element 1, what do we have? Or element 2 or element 3? Well, if we look for that, this guy here, the shape of these matrices and the entries depend on what? Kx, Ky, L, and W. And for elements 1, 2, and 3, L and W are the same, 10 centimeters. K is also the same, 1.4. Therefore, that contribution is going to be the same. Okay? That is going to be what? That is going to be the exact same thing. And I guess you can see that here. Right? You clearly see that the entries are the same. The only thing different for them are these matrices are between which nodes. So here the way we numbered the nodes is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We went row by row. And so for element 1, this is between nodes 1, 2, 4, and 3. And please pay attention, this is not 1, 2, 3, 4, it's 4 and 3. You go around the edges and come back. Okay, so you start 1, 2, 4, 3. You don't go 1, 2, 3, 4. You have to preserve the order of the nodes. For element 2, again, if you look at it, that's what? 3, 4, 7, 6. And for element 3 is 4, 5, 8, 7, as you can see here. Right? So that is very important. You keep track of the nodes that these entries are written for. Smallest mistake here can easily change your global K matrix. So what about elements 4 and 5? Well, for elements 4 and 5, if we go and look, this is again what? This is the shape, right? It depends on Kx, Ky, A, and A. Also, it depends on betas and deltas, right? It depends on beta and delta here. So if we go and take a look here, these are the K's for 4 and 5. Now the A's for them is the same, the K's for them are the same, and apparently the combination of deltas and betas, the subtraction for them and the product for them, turn out to be the same here for elements 4 and 5. Because remember, betas and deltas, they depend on the location of the nodes, right? If you remember back here, betas and deltas, they depend on the x's and y's of the nodes. And here, for elements 4 and 5, the x and y of the nodes are different. But when you calculated beta and delta and multiply together, raise them to the power and so on in this matrix, it turned out that the overall shape is basically the same. And again, look at the order, 2, 5, 4, and then the other one is 5, 9, 8, okay? So please pay attention to the orders. So these are the contribution from what? From the conductive portions, the Kx and Ky. And now it is time to look at what? The other portion for conduction, which was through the convective boundaries. So basically this guy here, right? And it depends on which edges are doing convection with the environment. So let's go ahead and take a look. So if we go and look here, right? Which elements of this guy are doing convection with the boundaries here, right? Is there any such a thing? And if we look, elements 2, 3, and 5 are the elements that are doing convection with the boundary here, right? Okay, through some of their edges. Let's take a look here. So for element 2, which is this element, the term we have is for 7, 6, 7, 6, which is this corner here, this edge here. So that edge is doing a what with the environment? It is doing a convection with the environment. And where is that? Well, the one that we are using here is this guy, actually. If you look at the shape, that's this one. And that is right here. Of course, it is doing convection with the environment. And what edge is that? If you consider the order I, J, K, right? So that is the top edge here, which is basically, if we go with the order that we have up here, it's this edge here. It is going from M to N, right? I, J, M, N. So that's MN edge for this guy. And for MN, the shape is what? Let's take a look at MN term. So that's this one. And it's this corner here, right? And you can exactly see that in this pattern here. Look, you see? Okay, that's the only edge from element 2 that is doing convection. And so we use that MN term, and this is K2 contribution. So now we have to add these two together to get the total K for element 2. What about 3? Again, for 3, it's the exact same thing. It's this top edge here that is doing it. So again, we have it on this corner. And then for element 5, again, it's this guy here. And for that one, if we go and look at the shapes, it's going to be this corner again, which is from 9898. And of course, it's 9898. And for the other one is 7878, as you can see. Okay. And so again, for K3, we have to add these two together. And then for K5, again, we have to add these two together to get the total KE for what? For that element. Elements of 4 and 1, they do not have any contact with the environment. They are here. They have no convection. So that's it. Summation of these will give us K for these individual ones. Now, what about the thermal loads? Let's go and take a look at the thermal loads. What do we have? Well, in this case, there is no constant heat flux, and there is no Q dot term. There is no way that it says inside this chimney we have a heat sink or heat source, and there is no constant heat flux. We forced it through any of these edges. So basically, these terms that have Q dot and Q double prime are 0. So the only terms that we have for any of these elements are due to convection, right? That's all it is. So basically, what you have is this guy here, right, for the rectangulars, and these ones down here for what? For the triangulars. That's all it is. Now, which edges did do convection? If you remember, again, they were these top edges of elements 2, 3, and 5. Therefore, for elements 2, 3, and 5, we have the thermal loads on edge 7, 6, 8, 7, and 9, 8, which are clearly the convective edges. So that's it. Now we're gonna assemble the K's and the F's together, and we get the giant F and the giant K. Of course, it is gonna have dimension 9 by 9, and this is 9 by 1. We set K times T equal to F, and we have some boundary conditions here. What are the boundary conditions? The boundary condition is at nodes 1 and 2, the temperature is 100. Where does that come from? Here. This is node 1, this is node 2, and they are here and here, and they are on this temperature of 100. So those are fixed boundary conditions. Therefore, we basically set those to 100, and then we have 8 unknowns and 8 equations, or 7 equations and 7 unknowns, which will get them from this portion of the matrix equal to this guy here, right? If we set them equal, then we should find these other temperatures here. And if you look at the temperatures, does that make any sense? Well, it says 1 and 2 are 100. Then we go to 3, 4, and what? 5. The temperatures are what? 70, 67, 51. And then we go to the convective edges. That's 45, 43, 40, and 32. So you clearly see as you go from the higher temperature of 100 toward the lower, which is 30, you go in this direction. Layer by layer, row by row, the temperature is dropping. And that does make sense. The other thing is, you see as I move from left to right, also, you see here, for these 3 and then for these 4, you see that the temperature is also dropping a little bit as well, and that's because of the distance, right? Because the distances of these edges from this constant temperature is increasing. So as I go this way, right, and look at the distance of each one of those basically nodes with respect to this, I'm increasing the distance. When the distance is increasing, it takes more time for them to reach the temperature, and there is temperature gradient. So not only there is temperature gradient in the y direction, there is also in the x direction. And therefore, in this direction, the temperature should go down, and in this direction, also the temperature should go what? Down, because the heat source is here. So you have drop in this direction and drop in that direction. And you clearly see that it does make sense. So if in one of these temperatures, you see that when you go from left to right, the temperature is increasing instead of decreasing, or when you go layer by layer, you go from here to here and then from here to here, you see that the temperature, instead of dropping, is going up. There is definitely something wrong. Okay, so you always look at the results and do a sanity check. Do not trust anything, because as I showed you, smallest displacement in any of these numbers will completely change your final results. So always check, make sure your results do make sense. Okay, hopefully this video was useful to you, and I will see you in my next lecture. Thank you.